Welcome to the module on the applications of recycled batteries. In this module, we will review the key results. Batteries power everything from small electronics to electric vehicles and energy storage systems, making them vital to modern technology and renewable energy progress. However, rising demand and improper disposal create challenges such as resource depletion and electronic waste. Sustainable recycling systems are essential to recover valuable materials and reduce environmental impact. The product life cycle outlines the different stages a product goes through, from defining requirements and development to recycling at the end of its life. In product engineering, considering the entire life cycle is essential to ensure sustainability and cost efficiency. Depending on the application, variations of the life cycle model may exist. The core objective of a circular economy is to maximize the efficient use of secondary resources, making it a key principle for sustainable production and consumption. Similarly, the battery life cycle includes the primary stages of production, development, vehicle integration, usage, and end-of-life processes such as recovery and recycling. Sustainability is essential as rapid battery expansion affects energy, transport, and digital systems. A sustainable battery value chain reduces environmental and social impacts through responsible sourcing, efficient production, and effective end-of-life management, while improving resource security via material efficiency and recycling. Extending battery lifetimes and enabling second life use lower reliance on materials and strengthen supply resilience. Clear sustainability standards also support economic stability, public trust, and long-term market growth, making responsible battery scaling a necessity rather than a choice. Effective battery end-of-life management improves sustainability by reducing waste, preventing environmental contamination, and conserving valuable resources. Recycling and second life use return critical materials to supply chains, lower demand for virgin extraction, and reduce associated emissions and land impacts. Achieving these benefits requires high collection rates, efficient sorting and recycling processes, and design for recycling with strong traceability. When implemented together, battery circularity strengthens resource security while minimizing environmental harm. Battery safety, health, and environmental risks must be managed throughout the entire life cycle, particularly during end-of-life handling and recycling. Spent batteries pose hazards such as fire, chemical exposure, and environmental contamination, with risks varying by chemistry. Lithium-ion batteries present thermal runaway risks, while lead-acid and nickel-based batteries involve serious toxic metal concerns. Effective risk management requires engineered controls, safe handling and transport procedures, and robust fire, ventilation, and waste treatment systems. Strong worker protection, training, monitoring, and regulatory oversight are critical to safeguarding people, communities, and ecosystems. Design for sustainability embeds environmental protection, safety, and circular economy principles into batteries from the start, shaping impacts across manufacturing, use, and end of life. Circular design, through standardized, modular, and easily disassembled systems with clear labeling and accessible state of health data, enables repair, second life use, and efficient recycling. Smarter material choices and improved safety features reduce resource dependence, environmental footprint, and operational risks. Supported by standards and producer responsibility, sustainability-oriented design strengthens safety, recyclability, and resource efficiency across the battery value chain. After their first use, batteries can enter a second life through different pathways. They may be repurposed, serving in new applications such as stationary energy storage systems or backup power units. Alternatively, they can be recycled, where valuable raw materials are recovered through thermal, mechanical, or chemical processes for use in new battery production. In cases where reuse or recycling is not economically or technically viable, disposal becomes necessary to safely manage remaining components or byproducts. Choosing between repurpose, recycling, and disposal depends on the battery's condition, state of health, and economic feasibility. These strategies collectively reduce waste, conserve resources, and lower energy consumption, supporting a sustainable battery ecosystem. Repurposing retired batteries mostly from electric vehicles allows them to be given a second life in less demanding applications such as stationary energy storage systems. Because each automaker uses different battery designs and operating conditions, these batteries age differently and must go through a systematic process before reuse. The first step is collection, where retired electric vehicles are sent to authorized treatment centers. There, the batteries are carefully removed and transported to facilities capable of recycling or repurposing them. This process may be managed by the vehicle manufacturer, the battery producer, or a third-party company. Next is screening, where the condition of each battery is evaluated. Engineers assess factors like chemistry, voltage, energy capacity, and remaining useful life to determine whether the battery can be reused directly or if it needs to be dismantled into smaller modules. Advanced diagnostic and data-driven tools help estimate the state of health and predict how much longer the battery can perform safely. Finally, in the reassembly stage, suitable battery modules are grouped and reassembled based on the power and energy requirements of their new application. Cooling systems and controllers are added or modified to match performance needs. Batteries with similar aging profiles are clustered together to ensure balanced operation and reliability. Overall, this repurposing process extends the lifespan of electric vehicle batteries, reduces waste, and contributes to a more sustainable and circular energy system. Second life battery energy storage systems reuse retired lithium-ion batteries as cost-effective, scalable stationary storage. They support grid and customer needs by firming variable renewable energy, enabling mini-grids in remote or developing regions, and reducing peak electricity demand through peak shaving. These systems can also provide fast, reliable backup power for critical infrastructure during outages. Despite reduced capacity compared with new batteries, second life systems offer economic and sustainability benefits, extending battery life and delivering reliable performance when supported by careful cost-benefit analysis. Second life applications are based on the fact that electric vehicle batteries are usually retired while they still retain a significant amount of usable capacity. Instead of recycling them immediately, this remaining capacity can be used in less demanding applications such as stationary energy storage. By reusing batteries, storage systems can be delivered at a lower upfront cost than new batteries. The economic value mainly comes from extending the asset life of the battery and postponing recycling expenses. However, the business case strongly depends on the costs of testing, repackaging, certification, and warranties. In addition, strict safety and performance standards must be met to ensure reliable operation and market acceptance. Second life batteries can improve sustainability by extending use before recycling, increasing the total energy delivered per unit of material and manufacturing impact. Batteries that no longer meet first use requirements may still be suitable for less demanding applications such as stationary storage, backup power, or renewable buffering, which can defer new battery production and reduce near-term demand for materials. The net benefit depends on the added processes required for reuse. Testing, diagnostics, disassembly, repackaging, and integration add energy and materials. Benefits are strongest when these steps are efficient and standardized, and smaller when they are complex, manual, or require major component replacement. Safety and reliability are essential. Second life systems must meet standards for electrical protection, thermal management, fire prevention, and transport, supported by clear liability and robust quality grading to ensure predictable performance and avoid incidents. Second life should be treated as a step that delays, not replaces, recycling. At the end of second use, batteries should enter controlled recycling streams to recover materials and prevent leakage into waste or informal disposal, supporting a more resource-efficient energy system. If the battery is damaged, unsafe, highly degraded, or its quality cannot be reliably assessed, recycling becomes the preferred option. Recycling is also the final pathway after the second life period, allowing recovery of valuable materials such as lithium, nickel, cobalt, and copper. Battery recycling has long relied on pyrometallurgical and hydrometallurgical methods. While pyrometallurgy efficiently recovers metals through high-temperature smelting, it consumes significant energy and generates harmful byproducts. Hydrometallurgy achieves high recovery rates through chemical leaching, but it requires large amounts of reagents and creates waste streams that must be managed. Recently, direct recycling has emerged as a more sustainable alternative, regenerating cathodes and electrodes with less energy and fewer chemicals. However, adapting recycling processes to different battery types and scaling up industrial capacity remain challenges. Closed-loop applications recycle materials from end-of-life batteries back into new battery production, maintaining a battery-to-battery cycle rather than downcycling into lower-value uses. By recovering and upgrading materials to battery-grade quality, these systems retain value, reduce reliance on mining, lower lifecycle emissions, and improve supply security. While maturity varies by battery chemistry and infrastructure, successful closed-loop systems depend on reliable collection, safe processing, strong quality control, and market alignment to ensure recovered materials can be confidently reused in new batteries. High-value, open-loop recycling repurposes recovered battery materials into functional products outside new battery manufacturing, focusing on application-specific performance rather than battery-grade purity. Degraded metals and carbon materials can be upcycled into catalysts, adsorbents, supercapacitor electrodes, and pigments, improving value capture while reducing energy use, waste, and emissions. By creating viable markets for mixed or lower purity streams, open-loop recycling broadens circularity, diversifies revenue, and reduces dependence on battery material price cycles, provided collection, processing, quality control, and market alignment are in place. Battery recycling provides clear environmental benefits by diverting hazardous materials from landfills and reducing demand for virgin mining and refining. Recovering lithium, cobalt, nickel, manganese, and lead conserves finite resources and often lowers energy use and greenhouse gas emissions versus primary production. It also reduces local pollution and health risks when handled through proper collection and controlled treatment. This prevents toxic releases, such as lead and acidic electrolytes from lead-acid batteries and reactive electrolytes or metal-bearing residues from lithium-ion systems, into soil and groundwater. Well-run recycling facilities mitigate safety risks, including fires from improper storage or disposal, and manage wastewater, dust, and solid residues using emissions controls and waste treatment. These safeguards are essential to avoid shifting impacts from one pathway to another. Recycling supports a circular economy by turning end-of-life batteries into inputs for new products. Higher recovery yields, improved purification, better collection, and design for recycling with traceability maximize displacement of virgin materials and strengthen a more resource-efficient energy system. In summary, material repurposing is becoming more important as battery use grows across mobility, electronics, industry, and energy systems. With rising volumes of end-of-life batteries, repurposing turns a waste challenge into an opportunity by keeping materials and components productive for longer and supporting a circular materials economy. Repurposing can follow closed-loop pathways, where recovered constituents are upgraded back into high-spec feedstocks, or open-loop pathways, where materials are converted into valuable industrial products such as functional carbons, catalysts, pigments, and adsorbents. This flexibility helps translate heterogeneous recovered streams into market-ready outputs. Sustainability matters because batteries are scaling fast and can amplify pressure on critical minerals, emissions, and waste if unmanaged. It provides the framework to keep growth responsible while preserving the benefits batteries deliver. Finally, safety and governance are the enablers. Batteries carry fire, chemical, and heavy metal risks across transport, storage, disassembly, and recycling. Strong standards, engineered controls, extended producer responsibility, and traceability keep flows regulated, protect people and ecosystems, and support stable markets for recycled materials. Thank you for your attention.